we talked about the applications of DC motors and generators, provided some references for your further studies. And then I focused on the Chapman book, talked about a simple rotating loop, which is between curved pole faces, as the very first type of DC machine that we can discuss. Then we talked about the fact that armature is the rotor here also in this type of machine, and a field would be on the stator. And we talked about how a voltage could be induced if you go ahead and basically rotate that loop of conductor. And we saw that the voltage that would be produced would be an alternative, inherently alternative voltage, which would go to a constant value and then sharply would rise to a negative value. In order to convert this voltage into a DC voltage, we would use commutation. So basically, the commutation is the act through which you have brushes. You can have for this basically application, if you have two brushes on the two sides and there are two semicircle basically loops that are connected to the two sides of the converter, this would give you the means to be able to get the DC voltage, which still has some sharp falls into the zero, but overall the average voltage would be a DC voltage. So this was the fundamentals of commutation. And we also talked about how a torque could be induced in this machine and provided the torque equation. So for both the torque and the voltage, we saw that if you increase the number of conductor loops, you would see the fact that basically your no matter how the construction of the machine is, the induced voltage would be a function of the phi, which is the flux per pole, as well as omega, which is the rotational speed. And it depends on some constant, which would be depending on how the machine has been constructed. Same concept exists for the torque. Torque is also dependent on the flux per pole, and instead of the omega or the rotational speed, here the torque would be dependent on the current inside basically the armature, and the same constant that you saw for the voltage. And then we went over basically what if you have a collection of these conductor loops or coils. So each coil in general could have multiple conductors inside, and then depending on the number of current paths, we could basically find out a general equation for the induced voltage in the machine, which would be Zp over 2 pi a. That's a constant. K, which would be then multiplied by phi and omega, where Z is the total number of conductors, and P is the number of poles in the machine, and A is the number of current paths. So the reason that basically this constant has a division over alpha is because there are some of the paths that are in parallel. So therefore, the voltages would just be the same voltage. So this was K for the case that omega is in radians per second. For the case that you want to represent the rotational speed of the machine based on RPM or revolutions per minute, you have a K prime constant that would be based off of equation 842. Also for the induced torque, we have the same K that we found for the case of the voltage. So in general, your tau induced would be K phi I A. In this session, I want to go over more of basically discussion on commutation and the problems that are associated with commutation. So commutation has certain issues that we want to discuss in here. The first issue would be armature reaction, which will cause in neutral plane shift and flux weakening. And we would have an L.di over dt voltage issue also due to basically the transition of current from a positive value to a negative value. You have an abrupt change in the current, and that causes in L.di over dt voltages. Let's go over these one by one, starting from armature reaction. So here I have a figure that is showing basically different times. The first figure is showing basically schematics of the simple machine that we just discussed. And here you're seeing the North Pole and South Pole on the stator. So this circle would be basically associated with the rotor. For the rotor, you have basically the armature windings on the rotor, as you can see. So on one part, you see that basically the currents are going into the page on the rotor or the armature, and on the other side, they're coming out of the page. But nevertheless, at this point, where you are supposed to have no voltage induced in the conductors, when you are rotating basically this cylinder inside this basically hole, then like in counterclockwise rotation in this case, then when the conductors reach basically this area, so theoretically there's no voltage should be induced on this. We call this the magnetic neutral plane, at which basically there would be no voltage induced in the machine. So due to this basically configuration, you can see that what you expect really in the machine is that the lines of magnetic field would be perpendicular to the surface of your cylinder, or this basically circle that you're seeing in here, and then come out perpendicular again. So they come from north, they transition into here, and then come out of the south pole, the basically magnetic field. So this is what we expect. However, when you're operating the machine, there would be some currents flowing in the armature windings. Isn't that so? So because of the currents inside the armature windings, you can see that there would be another magnetic field produced by the armature winding currents. As you can see, the flow of the current on the left-hand side here on figure C, on the left-hand side, using the right-hand rule would be in a way that this is showing basically the closed path associated with the magnetic field originated from the current inside the armature. And on the right-hand side, you can see that the direction would be clockwise. So here we have a counterclockwise rotation associated with a closed path of the magnetic field of the armature. Here we have basically a clockwise path, as you can see, closed path. All right, so what does this second magnetic field associated with the armature windings do? What it does is that you can see at some points, the overall magnetic field coming from the summation or the vector summation of both the stator and the rotor, which is on the armature, would cause basically a magnetic field that would sometimes be bigger. So the flux would be bigger in here, and the flux density also at this point on the, let's say, northeast, as well as the southwest. Okay, you can see that at these points, the overall flux is becoming more, or the magnetic field intensity is becoming more. And this will result in basically in the what we call neutral plane shift. So the original neutral plane was supposed to be here. This is the old one. But because of this effect of the armature, we see that the new neutral plane would have basically shifted from what you see compared to the original neutral plane. This original neutral plane happens when the machine is at no load conditions, when there is no current existing in the armature windings. But when there is a current existing in the armature winding, whether in the form of a generator or a motor, doesn't matter. In both cases, basically you would have a neutral plane shift. This plane shift, based on the Lenz's law and the electromagnetic rules that we already studied, is in a way that for generator operation would be in the direction of motion, So you can see that here, based on the fact that your omega is counterclockwise and your neutral plane has shifted to the left, what would be the operation of this machine? Is it a generator or a motor? Where in the motor, we're expecting the direction of basically neutral plane shift would be opposite the direction of the motion of the motor. Can you tell me, in this case, we are a motor or generator? It would be a generator, right? Correct, because that's in the direction of motion of the machine. So what would happen in this case when you have a neutral plane shift? That would cause in sparking in the machine. And why is that? Remember, in the operation and the commutation basically fundamentals that we studied in here, the commutator is supposed to basically collect the basically voltage in a way that it would result in a always positive or positive average. And that basically the transition from a positive into a zero happens right when these semicircles are transitioning. That the transitioning basically through that neutral plane. So at the neutral plane, we are expected to see a zero voltage. But due to this neutral plane shift, at that point, when we're supposed to see the zero voltage, we're not seeing a zero voltage. So overall, you would have some voltage on the brushes at that point, and that abrupt change causes that sparking in the machine. What would be the effect of the neutral plane shift caused by the armature? Now, there is another basically impact associated with the commutation, and that would be the flux weakening, the overall weakening of the flux in the machine. And that's because of the fact that in the machine, we see that all magnetic basically materials are working based on a curve. So we cannot say that all machines are working linear. No, magnetic materials always have a nonlinear feature. We saw that phi versus F, or the magnetomotive force, was like a straight line up to a certain point, and then we would go into a saturation, right? So because we want to operate the machine in its maximum possible potential, we always try to basically operate it at the close to the knee point. Here's the knee point when we are transitioning from a linear curve into a saturated curve. So here, that's usually when we are operating the machine. So the phi that here exists in this air gap, and the flux density that exists in this air gap is supposed to be ideally a constant value, which is close to the value shown through this knee point. Does that make sense? So we want to operate the machine at this point. However, you can see that when you have this neutral plane shift, at some point, the magnetomotive force is becoming more northeast and southwest, for example, in this figure. All right, so this means that basically at some points, we are going extra in terms of magnetomotive force with respect to what we expected. We're going this much more, but because of the saturation, basically we would get only a little increase in the phi. This overall results in reduction. The net result is that the total average flux under the entire pole face would be decreasing. There is another figure in here that shows this. Basically, you're seeing that this is basically the original case when there was no weakening in the flux. So you would have your neutral point right here. There is a transition to zero and then to a negative value in terms of magnetomotive force. But here, you can see that you were supposed to, if the curve was linear, you were supposed to go this far and then come back again negative this far. But you're not doing so because of that saturation that is happening. So instead of basically the overall curve that you can see here that has some dashed basically areas, you would see the peak to be less. And overall, you can see that the flux per pole is not really constant the way that you wished it to be. So in here, in figure A, the upper figure, you can see that a very large area, we have the phi and F, or magnetomotive force, to be both basically constant values in a good large area. But here, you can see that the net F is going higher. So if you just basically normalize both F and phi curves, you can see that the net F is going higher, but the phi is not going as high as you wished because of that overall weakening. So this causes the overall weakening, which means that when phi becomes smaller, you have less voltage in the generator and you have less torque in the motor, right? That's the basically flux weakening effect. Now let's go to the L.di over dt voltage problem. So during the commutation, a conductor, when it passes through the neutral area, the neutral plane area, then its current gets reversed, right? So for example, if the conductor's current was 200 amps, then it has to go to minus 200 amps in a very short period of time when it's passing through basically the neutral area. So during commutation, in a very short amount of time, the direction of the current will reverse. In this example, you can see that we have 200 minus 200 that over this duration, which is 0.0015 seconds, di over dt becomes around 267 basically amps per second. So even with a small, tiny inductance inside the conductors, you can see that you could have a large voltage basically associated with this effect of L.di over dt voltage, and that causes, again, sparking at the brushes in the machine. So that's the effect of L.di over dt, which is not really desired. All right, so we talked about briefly the problems of the commutation. Armature reaction and L.di over dt voltages. Armature reaction caused neutral plane shift, caused overall flux weakening, and L.di over dt voltages cause also sparking. So neutral plane shift also causes sparking. So both of these are causing some issues for us in the machine. In order to basically correct these issues or solve these issues, so there are some methods that do exist. The very first method that could seem reasonable for us in the first place and was basically used back in old days is just to shift basically the commutator or the brushes a little bit to the left or to the right, depending on how the neutral plane has been shifted, right? So when you see the shift in the neutral plane, that was the first basically solution that people came up with. However, there are some issues with this brush lift. The first is that really how much this neutral plane is shifted depends on the load, because it depends on how much current is inside the armature winding, right? So it's load dependent. If there is no load in the system, there would be no shifting. The more the load is on the machine, whether in the form of a generator or a motor, you will see that the neutral plane would shift more. So depending on how much current is in the armature. So this is not an ideal solution, because somebody needs to sit there always all the time and try to basically shift the brushes in a way that is load dependent, and load can change all the time in the operation, right? And also we know that the direction of the shift of the neutral plane is reversed between the motor and generator applications. In many, basically most applications, we can use the machine both as a generator or as a motor. So depending on whether we are using it as a generator or a motor, we need to pay attention to how we're shifting. So that's another thing that we need to care for. There is another issue. We talked about the overall magnetomotive force of the machine was weakened by this whole armature reaction, right? So if you want to look at it from a vector perspective, if this is the F associated with the pole, then the armature reaction due to this neutral plane shift would be a vector like this, which would basically cause in an overall net magnetomotive force of F net like this. This is the case that you have not shifted your neutral plane. But when you do shift your neutral plane, and you just compare this to the case that you have not shifted that, you can see that there is even more basically weakening, and your F net becomes even less than the time that you had when you had no shift, basically. So overall, this is not a desirable solution. So compared to the case that neutral plane was not shifted, it causes even more weakening of the overall magnetomotive force. Overall, this is an obsolete method, except for very small applications, which are always running at a certain loading conditions. When there is no load change, then you can use this method to get rid of the sparking associated with the commutation. There is another method, second method, which is used for like medium-sized motors or medium-sized machines. We use what we call commutating poles or interpoles. So what it does is that we put basically windings on the neutral plane like this, and we pass the current in these windings to be proportional to the current of the armature. So armature is in fact in series with these windings. So in other words, the current in these windings would be proportional to the current of the machine. So it would be proportional to the load. So if the load becomes zero, these would be zeros also. If the IA becomes more, the effect of these windings would become more. So this method is used only in the area that is associated with the commutation. You can see that commutation happens on the neutral plane. The magnetic field associated with these windings would basically work mostly for the conductors that are passing around your neutral plane area while rotating. it will not affect basically any of these windings that are far away from the neutral plane. So they only affect the conductors that are about to go under commutation. In other words, they can only cancel the L.di over dt voltages. So mostly what they do, these basically commutating poles or interpoles, what they do is that they cancel the L.di over dt voltages by producing a magnetic field that would overall result in a reduced voltage induction at the neutral plane. So the reason that we have basically these sparking in L.di over dt voltages is that there would be some voltage associated with this phenomenon, right? L.di over dt is the voltage across across basically the inductor L. So we're trying to counteract that voltage through basically the magnetic field that we put on these what we call interpoles. This method can be useful, but because these magnetic fields are not really doing anything about the conductors that are far away, the overall flux weakening due to armature reaction is still unaffected. So we still have that flux weakening. The figure is showing interpoles that are created through the current in series with the armature, as I mentioned, which makes their effect proportional to the load. So that the good thing is that the operation is proportional to the load. Flux from the interpole must produce a voltage that opposes the existing voltage in the conductors in the commutation area. And the use of commutating poles or interpoles is very common, especially for medium-sized general purpose motors that have sparking problems. And they just live with the flux weakening effect. We said that this method is not doing a lot for the flux weakening. The third method is basically using compensating windings. That's is used in very high power, heavy duty machines to completely cancel the armature reaction. However, they cannot still cancel the effect of L.di over dt voltage. Therefore, heavy duty machines will still require the interpoles. So we're adding the, still they need the interpoles to cancel the effect of L.di over dt. However, they can cancel the effect of your neutral plane shift using the compensating windings. These compensating windings are in series with the rotor windings. So if you look at this basically rotor, these are the conductors associated with the or the windings of the rotor. These outer windings are associated with the compensating windings. So their effect is reversed. So the current that is flowing in these compensating windings is reversed compared to the current that is existing in the armature windings, as you can see. But magnitude-wise, they are basically proportional to both of these. I mean, these are the currents of the armature itself, but the currents inside these compensating windings is opposite, but is proportional. Overall, basically, magnetic field is proportional to the current that is existing in the armature, so that the overall operation would be load dependent, if that makes sense. So here is the effect of compensating windings. So you can see that we have the F, or the magnetomotive force, associated with the poles. So this is associated with the poles. The FR is associated with the armature reaction. And the CW is associated with the compensation windings. So if we are able to make that F of compensation equal but opposite to FR, which is coming from the armature reaction, we would be able to make the F net equal to F pole. And this is basically the desired case which we want to have. And we get this original desired magnetomotive force curve that we wanted. Let's go over the power flow and losses in the DC machines. So first thing is efficiency. We know that the efficiency in the machine is the output power over the input power times 100 to make it in percent. And the difference between the input power and the output power would be the losses, right? And the losses in the DC machines are coming from the copper losses, from the brush, from the core, from mechanical losses, and from stray losses. So we talked about these briefly also when we talked about fundamentals of rotating machines. We talked about all of these. So the same concept is in here also. The electrical or copper losses can be associated with the armature. So if RA is the overall resistance of the armature, and IA is the current inside the armature windings, the PA or armature loss would be RA IA squared. In most cases, the field is going to be created on the stator using an external winding. So that winding has its own resistance of RF, has its own current, the current that goes inside that. So that would be the field losses. So you have to add these both together, PA for the armature loss and PF for the field loss when applicable. The brushes, so there would be some voltage that is falling on the brushes at the moment of commutation, and that is almost a constant value equal to VBD, B of the brush drop loss would be PBD, and IA would be the armature current. Okay, so that's another factor that needs to be added to the losses. We have core losses. The core losses in the machine are in the form of hysteresis and eddy current. These losses have been described in chapter 1 of the book as well, and we discussed that also in our notes briefly at the beginning of the course. And then we have mechanical losses again. The mechanical losses would be in the form of friction, would be in the form of windage. Friction is when two basically solid objects are in contact. Windage is when the solid basically object is has a friction with the air. And we have stray losses or miscellaneous losses that we discussed this before. No matter how much we try to model the losses as accurate as possible and using measurements as basically delicate as possible, there would be some losses that we miss, and that would be called the stray losses. So if you want to look at the flow of power and losses in the DC machines when they are working as a motor versus basically a generator, here A is associated with a generator. On the input side, we are applying tau or a torque times omega m. That becomes the input power. Then there would be some stray losses deducted, and then mechanical losses associated, and then core losses. After these, at this point, we call this power the converted power. The power that is converted from basically magnetic field into electricity. So here, the difference between tau is tau app versus tau induced. Tau induced is the electromagnetic torque that has been induced in the machine. That becomes also equal to EA/IA, where EA is the internal voltage produced by the machine, and IA is the armature current. Then we would be subtracting the RIDO losses, which are the copper losses, and then the output power would be given VT times IL. That would be the terminal voltage times the load current. That becomes the output power that we deliver to the load. When the machine is working as a motor, then we provide electric power to it, VTIL. Then RI2 losses, the copper losses. Here we get the converted power. And then core losses, mechanical losses, stray losses will be subtracted until we've applied the output power to the mechanical load, tau app times omega m. So the flow of power is exactly reversed if you want to compare these two with one another. If you reverse the flow of power, you go from generator to motor or vice versa. So P converted can be described both as tau induced time omega m. Tau induced is the electromagnetic torque induced. Omega m is the rotational speed of the machine, or can be also described through EA/IA. EA is the voltage induced on the windings of the machine, or the what we call internal voltage in the machine, and IA is the armature current. So keep that in mind. The following information is given about the simple rotating loop shown in figure 8.6. 8.6 figure is the same famous figure that you also have in your presentation slides. That's the loop, conductor loop. So looking at that, so B is 0.8 Tesla. That's the flux density, right? L is the length of each side of the conductors, 0.5. R is 0.125. What is that? That is the radius, right? The radius of the circle associated with that loop. So if you look at that cylinder, the cross-section of that cylinder would be a circle which has a radius of 0.125, and your conductor bar is going to be carved into that cylinder, around that cylinder. So going from one side, coming from the other side. VB is the battery voltage. In that figure, we had a battery at 24 volts. R, 0.4 ohms. That's basically the the resistance of the circuit, which could be the resistance of the battery, the internal resistance of the battery, and the rotational speed is 250 radians per second. Let me bring that figure from the notes and put them side by side. So when we have these conditions, if we are applying this voltage and we're closing the circuit, is the machine operating as a motor or a generator? Explain. We know that because of the speed of the machine, there must be a voltage induced in the windings. Isn't that correct? So that E induced would be, so let's see how much voltage is being induced. The voltage is 2 times, and this is coming from where? So E induced would be 2 times RLB omega, right? So I'm bringing that from here. So let's see. 2 times, what is R? R is 0.125. What is L? That is 0.5. What is omega? That's 250. And what is B? That's 0.8. How much is that? So let's calculate this. We have RB equal to 0.8 Tesla and L equal to 0.5 meters, R equal to 0.125 meters. We have a VB that's 24 volts. R is equal to 0.4 ohms. And omega is 250 in radians per second. So we have E induced is equal to 2 times R, L, omega, B, right? So this gives us the voltage in volts because everything is in SI. So when we run this, we get 25 volts. So we have 25 volts. So we have 25 volts induced in here. Since the voltage here is more than the 24 volts, so in our circuit, we would have, so we have VB, which is how much? 24. This is R. And we have a voltage equal to 25 volts, basically created in here, right? This is E induced. Now, because of this, the direction of the current in the armature would be this way. So I armature would be 25 minus 24 over R, which is 0.4. That's 1 over 0.4 or 10 over 4. That's 2.5 amps, right? So does this prove that the machine is working as a generator? Yes, because it's providing power really into this R, as well as it's giving power to the battery. So your machine is working as a generator. So that's how we can explain that. So IA would be equal to, in general, VB minus E induced over R, right? Which, in this case, that IA gives us a negative value. That's because I took basically, in other words, I took the IA direction to be the other way. So here, if I take the IA direction to be the other way, that comes out as minus negative value, and that proves that the machine is working as a generator. So this is the first part. What was the second part of the problem? Part B, what is the current flowing into or out of the machine? What is the power flowing into or out of the machine? So that's basically E induced times IA is the power out of the machine, right? So I write it here as P is going out of the machine. Since the power going out of the machine is positive, then this is another proof that your machine is working as a generator. Or why don't we basically, because this is a generator now, I'm going to change the direction of current. Take it this way. Just come back here. This would be E induced minus VB. Current out of the machine. If IA is greater than 0, then we know that the machine is a generator. Else, we know that the machine is a motor, right? So this is part A. Part B, because of the changes that we made, that has to be now positive, E induced times IA. And this was basically part A and B, both together. P out is the power out of the machine, which should become now a positive value. And part C, if the speed of the rotor were changed to 275 radians per second, what would happen to the current flow into or out of the machine? So this is when you are changing omega. So let's call this omega 1. And then omega 2 would be how much? Well, your omega 2 would be 275. 75 radians per second. So this is omega 1. This is E induced 1. This is IA 1. And this is P out 1. This is condition 1 overall. So let me put these side by side. So this is P out in condition 1, which is a generator. Now, in part C of the problem, we're needing to basically find E induced 2. In the second condition, that would be omega 2, IA 2, omega 2, IA 2, 2, all 2s. Now, in the second condition, we have still P out is going to be positive, which means that still the machine would be a generator. Let me call these omega A, omega B, associated with parts AC, omega C and omega D, okay? This is associated with part D of the problem, which is 225 radians per second. So this is E induced A, omega A, E out A. Then this becomes E induced C, part C. A and B were kind of the same. This is omega C, IAC, C, IA part C, 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 and C. Now, in part D of the problem, we're going to change the speed to omega D, right? So this becomes omega D part D, 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 and D. So this gives us the whole solution. I think, yeah. Part A, we were a generator. Part C, we are generator. But in part D, how much is the voltage? 22. So I'm expecting the current to become, this is the induced D. In part D, we become a motor in this problem because we're reducing the speed.